Hello, everyone. So in this session, we'll be doing some coding about transfer learning. We'll explore transfer learning first, and then we'll train a neural network model from scratch, and then we'll see how using a pre-trained model can significantly boost performance. And as usual in my notebooks, there's some preliminary, so pre-importing some stuff. Now, again, we're going to be building our simple CNN model for comparison purposes so that you appreciate transfer learning. I'll skip the detailed explanation since I've already covered this in a previous lecture and notebook. You may refer to that. To keep training and inference efficient, I'll only be using 5K samples for training and 1K for testing. Still a good solid sample size for our purposes here. So I'm going to be preparing the data. Not going to explain too much about it, but at a high level, I'm going to be setting the seed so that our results are consistent. I'm going to be making use of CIFAR10 dataset, which I've also used in the previous lecture and notebook about CNN. And then I'm going to extract the random 1K samples, as I mentioned. And then some transformation here, make it from 0 to 55 to 0 to 1 scale instead. And then I'm just going to convert the class vectors to binary class matrices here. Or I mean multi-class. Sorry, it's a multi-class output here because it's CIFAR10. There's 10. Yeah. Then if you check the min-max values, you have 0 to 1. Now let's build the model. And I won't be discussing too much about this because this is the same that we have in the CNN module. So if you check here, our scores are about 62% for the train set, and the val set or your test set is about 52%, right? That's our comparison. So the same data set we're going to be using later on. Okay, intro to transfer learning. Transfer learning leverages features from a model trained on one problem to tackle a related task, like using cat pre-detection model to help identify other feline creatures such as lion and tiger. This approach is especially useful when data is limited, making training a full model from scratch impractical. So here's the transfer learning workflow. Typical workflow in deep learning transfer learning involves reusing a pre-trained model. Here we import the layers and weights from an already trained model, and I'm going to be showing an example of that later. We're going to be freezing the layers. We lock these layers to preserve their learned information, essentially the previous weights. We still utilize the trained model. We set trainable equals to false. You'll see that later. Next is we add new layers. We stack new trainable layers on top of the base model that we use to adapt to the existing features. Sorry, we use the new trainable layers so that we adapt the existing features to the predictions on our specific data set. Because it's a new data set, a new example now, we have to do some customization. So this is where it comes from. This is optional. The next part, it's fine tuning. We unfreeze part or all of the model and training it on new data with a low learning rate. This can further refine features, enhancing performance for the new task. And lastly, we of course now train it on the new data. After we've done all of these things, right? We want to train it to our new data set. Now, let's build our base model. And for this one, I'm going to be making use of MobileNet V2. It is a deep neural network architecture designed by Google for efficient mobile and edge device applications. It builds on its predecessor, MobileNet V1, obviously, by improving both speed and accuracy while minimizing computational costs, making it ideal for devices with limited resources like smartphones and IoT devices. I'll be using this model in this notebook because it's very lightweight and Google Collaboratory's memory limit can handle it. Normally, I'll be making use of my own laptop and I'm gonna utilize a bigger model, but since I wanna make this more accessible to more people, I'm trying to use Colab and let's see what I can squeeze out of it. So with lots of testing, this is one of the models that I can utilize that works for the specific data set with the sampling and all of that. Anyway, this is one of the models that are available in Keras, one of the pre-trained models out there. Normally, again, I'd make use of more powerful ones. So this is how you import it. Very simple, right? You already have it here. So you can see that it has how many weights? Lots of scrolling. So you have total parameter size of about 2 million, right? That's a model size. Now, we're going to be doing transfer learning here. Of course, we have to do some data pre-processing. So we will be resizing our input images because MobileNet V2 works on images that have higher resolution. So initially, our dataset, the Sephartan dataset, is 32 by 32 by 3. But I'll just scale it up. So from 32, I'll make it 96. So this is how you do it. Now, I'm going to be using the same pre-processing that they've done in the original model. So this is how you use that. Use the pre-process input. It's one of the things that we have imported as well. If you check the min-max, it's negative 1 to 1. So that must be the scaling that they have done in the original model. Okay, now second step, we freeze layers. And fine-tuning is optional, as I mentioned. So the layers in a neural network model have two types of weights. You have the trainable and non-trainable. Trainable, as the name implies, you train it. When you train the model, those weights get updated to minimize the loss. Whereas non-trainable weights, there are also parameters that you have in the model, but you don't train them, you don't update them. During forward pass, those weights are used as is. You could also call these attributes in Keras just to double check. I'm also including the code snippet for doing fine tuning. If you want to retrain specific layers or freeze or unfreeze certain parts, this is what you do. You just replace with the target layer's name so that by doing this, those layers are updated. Note that first thing that you do here is to set the trainable to equals false. That means the whole base model is not trainable. And then after that, we're manually making some of the layers trainable. That's what's happening here. But we're going to skip fine tuning here. We're just going to freeze the base model as is, and we're going to stack the dense layers. Good. So we have added a few layers after the base model so that it can adapt to our new data set. So again, I've set the dot trainable attribute to false. And then I've added the flatten, some drop out layer. You could remove that, but generally drop out is good. You can tweak the values if you want. Now I'm adding the dense layers here. So there's 1 to 8, 64. And then finally, the 10. The last layer is 10, of course, because you have 10 classes. And the activation is softmax. And so if you check here, the total number of parameters now by adding the dense layers would be 3.7 million. And the trainable parameters is 1.4. The non-trainables are about 2.2 million. Now, you compile it after you've done preparing the model. You compile it. So 10 epochs as well, same data set, but we had to scale it up. Now, you can see that still very fast, right? If you compare the training time with our previous CNN model, you'll see that this is also quite fast, even though we're making use of a bigger model. And then at the end of it, we got 99% accuracy for the train set and 83% accuracy for the test set, which are much higher than the manually trained CNN model. I'll scroll up a bit so you can see the time it took for us to train the CNN model. Of course, it's a small model, so it's very fast, right? But now, see the size difference from like a very small CNN model, like about 90K parameters. We now have like 3 million in terms of size, in terms of parameters, but it's still quite fast because we're not actually training the base model. We're training the additional dense layers, which is also heavy, right? Because of the 1 to 8 and 64 and 10 that we're seeing here. But with just few modifications, we're already getting very good performances out of it. And that's the power of transfer learning. So if you want to see the graph here, you see this, right? Quite stable, right? In the first epoch, we already got very good test and train accuracies, apparently. And that's it for transfer learning.